Number 83. How about this series? It has 5 to the n on top, and that in itself is a very large function. 5 squared is already 25. 5 cubed is 125. Then the 4 to the n and 3 to the n decide to combine their powers, and if they combine their powers, is it enough to make these fractions so small that it converges? Well, I'm not really familiar with this function, so what I'm going to do is go over to the graphing calculator, take a look at the graph, and see what's going on. So go to y equals, and make sure I put the 4 to the x and 3 to the x in parentheses. For the window, it can start at 0, and let's just go out 10 terms. And for the y value, that could start at 0, and let's go out to 10. And it looks like the graph is growing pretty rapidly. So notice that when n is equal to 1, it equals a 0.9083. In order to have a series converge, all of the numbers need to be very small. Well, 0.9083 is less than 1, so that's good news. But as you progress from there, it just gets bigger and bigger and bigger. Now this graph doesn't actually prove anything because there's no guarantee it's going to go up forever just by looking at the graph. There may be a point where it turns around and comes back down. So can we prove that it's just going to keep going up and up and up to infinity? All right. So basically my question is this fraction going to be bigger than or equal to 1? Because if so, when you add up numbers that are bigger than 1 and you add up a whole bunch of them, that's going to diverge. Or I could rewrite that question, just multiply to get rid of the denominator. So multiply both sides by 4 to the n plus 3 to the n. So is this statement true? So for n equals 1, it would not be true. So if you try n equals 1, that would just say, is 5 bigger than 3 plus 4? So 5 bigger than 7? No, that's not true. What about at 2? Then that would say 5 squared is bigger than or equal to 4 squared plus 3 squared. And that would be, is 25 bigger than or equal to 16 plus 9? And that is true because the inequality does have the equals on it. So 25 is bigger than or equal to 25. It's true. And now we're going to do something a little bit different, and that is called, let me just draw my little picture. So we proved that it's true for n equals 2. And basically the way this proof goes is if you know that it's true for n equals 2 and at any point, so this is supposed to be a little ladder right here. So at any point you know that it's true. So let's say you know it's true for k. And you're able to prove whenever it's true for k, it's also true for the next step, k plus 1. So that means you have your base step at 2, and you've proved that anytime you're at one step, you're able to go up to the next step. So that means you could go from 2 to 3, and from 3 to 4, etc. And you could go up the ladder forever, which means that this would be true for all n bigger than or equal to 2. Okay, so I've actually proved the base step over here on the left side. Now I just need to prove this step, which is called the induction step. So if it's true for k, prove that it's going to be true for the next step. I just need a little more space right here. Excuse me while I sweep up the floor. And here we go. So this is called a proof by induction. Okay, so assume that it's true at level k. So assume that 5 to the k is bigger than or equal to 4 to the k plus 3 to the k. Then I want to get to the k plus 1 level. So I'll multiply both sides by 5. So 5 times the 5 to the k is bigger than or equal to 5 times 4 to the k plus 5 times 3 to the k. So on the left side, we definitely have the 5 to the k plus 1. So that is taking us up to the next step. And then on the right side, I guess I didn't need to rewrite that. Hold on. And then on the right side, so this number is bigger than, so if you look at this 5, if I change it to a 4, well, 5 is bigger than 4, so that means that this inequality here is true. So if I change that single 5 to a 4, then this is going to be 4 times 4 to the k. And then do the same thing with this 5 right here. If I change it to a 3, well, since 5 is bigger than 3, that means that when I change the second pinkish purplish 5 to a 3, that means that the inequality is true. And then if you look at the beginning part, it says 5 to the k plus 1 is bigger than or equal to, and then on this side, there's 4 to the k plus 1 plus 3 to the k plus 1, which means that I just proved if it's true for k, then it's true for k plus 1. That means it's going to be true all the way up the ladder, which is the mathematical proof that this graph I was looking at just keeps going up and up and up, and it's never going to come back down. And then that means that the answer to this question is yes. So for n bigger than or equal to 2, all of the fractions would be bigger than 1. That means that it diverges.